Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Spitzer's Legacy: Unveiling the Hidden Universe. In the vast, dark expanse of space, where light from distant stars and galaxies travels billions of years to reach us, the Spitzer Space Telescope has served as one of humanity's most powerful tools for exploring the universe. Launched by NASA in 2003, Spitzer was the fourth and final addition to NASA's Great Observatories program, which included the Hubble Space Telescope, the Compton Gamma Ray Observatory, and the Chandra X-ray Observatory. While each of these telescopes offered unique insights into the cosmos through different wavelengths of light, Spitzer focused on the infrared portion of the spectrum, unveiling aspects of the universe that were previously hidden from view. Spitzer's journey began with its launch on August 25, 2003. Aboard a Delta II rocket from Cape Canaveral Air Force Station. Named in honor of the American astrophysicist Lyman Spitzer, who first proposed the concept of space telescopes, Spitzer was placed into an Earth-trailing orbit around the Sun. This innovative orbit allowed it to drift away from Earth's thermal interference, providing a clearer, colder environment ideal for infrared observations. Infrared astronomy is crucial because many objects in the universe emit most of their energy in the infrared spectrum. This includes cold, dusty regions where stars and planets form, the cool surfaces of planets and asteroids, and distant galaxies shrouded in cosmic dust. By observing these wavelengths, Spitzer could penetrate the veils of dust and gas that obscure visible light, revealing the hidden structures and processes within. One of Spitzer's early and significant achievements was its study of star formation. Stars are born in dense molecular clouds of gas and dust, regions that are opaque to visible light but transparent in the infrared. Spitzer's sensitive instruments, including the Infrared Array Camera, IRAC, the Infrared Spectrograph, IRS, and the Multi-Band Imaging Photometer for Spitzer, MIPS, allowed astronomers to peer into these stellar nurseries. Spitzer's observations provided detailed images of protostars and the disks of material surrounding them, which would eventually form planetary systems. In 2004, Spitzer captured one of its most iconic images, the Mountains of Creation. This image showed towering pillars of gas and dust in the Eagle Nebula, reminiscent of the famous pillars of creation captured by the Hubble Space Telescope. However, Spitzer's infrared vision revealed much more. Inside these pillars were dozens of newly formed stars, previously hidden from view by thick layers of dust. This discovery offered invaluable insights into the processes of star birth and the early stages of stellar evolution. Spitzer also played a crucial role in the study of exoplanets, planets orbiting stars outside our solar system. Before Spitzer, most known exoplanets were discovered through indirect methods, such as observing the wobble of a star caused by an orbiting planet. Spitzer, however, made groundbreaking direct observations of exoplanets by detecting the infrared light they emit. One of Spitzer's notable contributions was the detection of weather patterns on exoplanets. For instance, Spitzer observed HD 189733b, a hot Jupiter exoplanet, and mapped its temperature variations, revealing dramatic differences between the day and night sides of the planet. In addition to exoplanets, Spitzer's infrared capabilities were instrumental in studying the distant universe. By observing distant galaxies, Spitzer helped astronomers understand the early stages of galaxy formation and evolution. One of the telescope's significant findings was the discovery of some of the most distant galaxies ever observed, dating back to when the universe was less than 1 billion years old. These observations provided critical data on how galaxies grew and evolved over cosmic time. The study of our own Milky Way galaxy also benefited from Spitzer's capabilities. By mapping the infrared emission from dust and gas in the galactic plane, Spitzer created detailed maps of the Milky Way, revealing its structure and star formation activity. Spitzer's observations helped refine the models of our galaxy's spiral arms and provided new insights into the distribution of stars and interstellar material. Another remarkable achievement of Spitzer was its contribution to the study of planetary disks. These disks of gas and dust, found around young stars, are the birthplaces of planets. Spitzer's infrared observations allowed astronomers to study the composition and evolution of these disks in unprecedented detail. For example, Spitzer detected signs of organic molecules and water vapor in the disks around young stars, suggesting that the building blocks of life are common in planetary systems. In 2009, Spitzer's mission faced a critical turning point. The telescope's cryogenic coolant, essential for cooling its instruments to the extremely low temperatures required for infrared observations, was depleted. However, rather than ending the mission, NASA initiated the Spitzer Warm mission, utilizing the telescope's 2 shortest wavelength detectors that remained functional at the warmer operating temperatures. Despite these limitations, Spitzer continued to produce valuable scientific data. During the Warm mission, Spitzer made several significant discoveries. One of the most notable was the detection of an asteroid collision in the young star system HD 172555. Spitzer observed the aftermath of the collision, providing evidence of how planetary systems evolve through such violent events. The Warm mission also continued Spitzer's exoplanet research, leading to the detection of small, rocky exoplanets and the study of their atmospheres. Spitzer's contributions extended beyond its primary scientific objectives. The telescope played a key role in the SETI Search for Extraterrestrial Intelligence Institute's efforts to search for extraterrestrial life. By observing star systems that had previously shown unusual radio signals, Spitzer provided additional data to help determine whether these signals could have an artificial origin. Although no conclusive evidence of extraterrestrial life was found, Spitzer's observations added valuable context to these intriguing signals. One of Spitzer's most profound contributions to astronomy was its role in multi-wavelength observations. By combining data from Spitzer with observations from other telescopes, such as Hubble, Chandra, and ground-based observatories, astronomers were able to create comprehensive views of celestial objects and phenomena. This multi-wavelength approach allowed scientists to study the universe in greater detail, revealing the complex interplay between different forms of radiation and matter. As Spitzer approached the end of its mission, its legacy became increasingly apparent. The data collected by Spitzer continues to be a valuable resource for astronomers, contributing to ongoing research and discoveries. The telescope's archive contains a wealth of information that will be studied for years to come, providing insights into the universe's most fundamental processes. On January 30th, 2020, after more than 16 years of groundbreaking observations, NASA officially ended the Spitzer Space Telescope mission. The decision was made as the telescope's orbit around the Sun had drifted too far from Earth, making communication and operations increasingly challenging. The mission's end was marked by a final command from NASA's Deep Space Network, placing Spitzer into a safe mode. The Spitzer Space Telescope's legacy is one of remarkable achievements and transformative discoveries. It expanded our understanding of the universe, revealing the hidden beauty and complexity of the cosmos in the infrared spectrum. Spitzer's observations provided critical insights into star formation, exoplanets, distant galaxies, and the structure of our own Milky Way. The telescope's contributions have paved the way for new infrared observatories, such as the James Webb Space Telescope. One of Spitzer's most enduring legacies is its impact on the study of exoplanets. The telescope's infrared capabilities allowed astronomers to study the atmospheres of exoplanets, detect their thermal emissions, and map their temperature distributions. These observations have provided valuable data on the physical properties and compositions of exoplanets, contributing to our understanding of their diversity and potential habitability. Spitzer's infrared observations also provided critical data on the processes of star and planet formation. By studying the disks of gas and dust around young stars, Spitzer revealed the conditions and mechanisms that lead to the formation of planetary systems. The detection of organic molecules and water vapor in these disks has important implications for the search for life beyond Earth, suggesting that the building blocks of life may be common in the universe. The Spitzer Space Telescope's mission may have ended, but its impact on the field of astronomy will endure for generations. The data and discoveries made by Spitzer continue to shape our understanding of the universe and inspire new questions and avenues of research. In conclusion, the Spitzer Space Telescope has left an indelible mark on the field of astronomy. Its infrared observations have unveiled the hidden beauty and complexity of the universe, revealing the processes of star and planet formation, the diversity of exoplanets, and the early stages of galaxy evolution. Spitzer's contributions have expanded our understanding of the cosmos and paved the way for future explorations. As we continue to study the data collected by Spitzer and build on its discoveries, we honor the legacy of this remarkable observatory and the insights it has provided into the wonders of the universe.